In our last lecture, we covered, in the lecture video, we covered vectors, force vectors, and some of the applications and operations of those force vectors. But then we also talked about another type of vector, which was a position vector. Now, I only talked about it briefly, right? We talked about 5 minutes, 10 minutes in the end. So it wasn't really meant to be a full explanation. But I did want to introduce you to them. So before we start, I want to talk about the difference between force vectors and position vectors, okay? So force vectors represent, obviously, forces. So that means that if I have two force vectors, and let's say that I'm drawing them proportional to their magnitudes. I'm going to have a force vector A, a force vector B. And these drawings, these lengths are proportional to their magnitudes. Which vector has a higher force? These are force vectors, so which of these two has a higher force? B, right? So because the force vectors are proportional to their magnitude, then I can say that the bigger the vector, so the bigger the magnitude of the vector, then the bigger the magnitude of the force. Now, those magnitudes represent forces, right? They're not distances. So you may have noticed in some of your textbook examples that you have something like a string or a cable, and then a force vector acting along that string or cable. That force vector represents the magnitude, the amount of force that's being applied to the cable, not the length of the cable. And here's where position vectors are different. Position vectors actually represent physical dimensions, all right? So when I explain position vector, I try to make a pretty quick explanation, but we're going to go into a little bit more detail today. Let's say that I'm dealing in 3D space. When I say 3D space, I mean an x-axis, a y-axis, and a z-axis, okay? So if I'm dealing in 3D space, and I have 2 points somewhere in this three-dimensional space, 2 points, I'm going to call this my point A, and I'm going to call this my point B, then I define my position vector as a vector that travels from one point in space to another point in space. And that space term is important, right? Because position vectors represent lengths or distances in space. So let's say that this point A is at coordinates xa, ya, and za. That's my coordinate. It can be whatever number you want to give it. And let's say that B is at coordinates xb, yb, and zb. So if I want the position vector that travels from A to B, what I'm essentially asking you to give me is the direction of A to B. And it's actually pretty straightforward, right? The position vector, which we usually represent with the letter R, the position vector from A to B starts at A and ends at B. So what I want to calculate that position vector is the difference. The difference in my x coordinate between A and B, the difference in my y coordinate between A and B, and the difference in my z coordinate between A and B. So what's your name?
Will.
Will. Let's start with Will. What is the difference, again, difference between A and B for the x coordinates?
xb minus xa.
That's correct. Thank you, Will. xb minus xa. So my position vector would be this difference along the I direction. Ray, what did the I vector represent? This I hat vector.
You mean the x, x whatever coordinate.
It's a unit vector along the x-axis, right? Good. So we have the difference in the x direction, or in the x position, in the x coordinate, in the I or x direction. We have the difference in the y coordinate in the j direction, where j represents the unit vector along the y-axis. And then we have the difference in the z coordinate in the what direction? K, right? Where k represents my unit vector along the z direction. If you don't remember, this little hat just tells me that I'm dealing with a unit vector. And a unit vector is essentially a vector with a magnitude of 1. That's why we call it unit vector. So this is my position vector from B to A. Here, because we're dealing with differences, displacements, the direction is very important. When I say that my position vector goes from A to B, I mean that my vector starts at A and ends at B. So tip of the arrow points towards B. Because of that, we're looking at differences between B and A. Now, what if I do the opposite? What if I ask you for the position vector from B to A? How would this equation here change? Let's go with you.
Wouldn't it just flip? So it'd be XA minus XB.
Exactly. Good. So XA minus AB, right? YA minus YB. And ZA minus ZB. Now, I don't want you to get too confused. When I say the vector from A to B, that means that my vector starts at A, ends at B. But because of that, you calculate it by taking B first minus A. So sometimes students get confused. They see AB and they assume it's going to be AB, AB, AB. It's actually the opposite. Okay. So the first subscript typically gives you the start point. The second subscript typically gives you the end point. So that's essentially a position vector in a nutshell. Madison, what's the difference in magnitude between these two vectors, AB and BA? In magnitude. So in other words, since the position vector represents a length, then the magnitude is essentially just that scalar quantity, that length. So what's the difference in their lengths?
They should be equal.
Exactly, thank you. They are equal, right? Because both vectors go from the same or travel between the same 2 points, and the magnitude of this vector actually represents the length between these 2 points. In other words, this length from A to V is just my magnitude R. Because that length is just my magnitude, that means that RAB and RBA should have the same magnitude. So if they have the same magnitude, but we're mixing some numbers around, what's the difference between these two vectors? Let's go with you.
Can you repeat the question? I'm sorry.
Yeah, it's okay. If we have the two vectors with the same magnitude, right? So what's the difference between these two? Like, we did flip these terms. What does flipping these terms give us? What does that make? The magnitudes are still the same, right? The distance, the length is still the same. So what's the difference between these two vectors, primarily? Not talking about numbers here. I'm just talking physically. Can somebody help him? Yeah,
Direction. Direction.
Exactly, the direction, right? So the magnitude is the same. So you're right, the difference in magnitude is 0. But really, the difference between these two vectors is the direction. One is pointing in one direction, one is pointing in the other. Now, I had an interesting... Something happened to the camera. That's not recording. Give me just a quick second to fix this, because this is not good. I'm going to need you to step out of your chair for a second. Thank you. This cable is not very good. Alright, that did not fix it. That's okay, I'll record tomorrow, so I should.
Oh, it's over now.
I did it! I'm a genius. Alright, it's recording. I hope that we didn't miss much. But anyway, the magnitudes are the same, so the difference is actually just the direction. Now, I had an interesting office hours conversation today where we did come up with something. The directions are different, and I had a student ask me, so where do I apply the negative sign, right? Because if the directions are different, then that means that RAB should be equal to negative RBA. But here's the thing. When we're talking about positive and negative signs, we typically express them in terms of your x, y, and z directions. So in this case, there is no negative sign, right? It's not that one vector will have a magnitude of, let's call this magnitude 8, and that this will be negative 8. That's not how it works, okay? Because these positive and negative signs actually refer, or we use them in the context of a coordinate axis. So you don't have to worry about positive and negative signs when it comes to magnitudes. Magnitude is a magnitude, all right? What you do have to worry is when it comes to the actual components in the x, y, and z direction. That's where your positives and negatives will come into play. And you see it right here. xb minus xa is actually just negative of this one, right? yb minus ya is actually just negative of this one, and so on. So the positives and negatives, leave them for your x, y, and z components, but don't consider them when you're talking about magnitudes, okay? Does that make sense so far? Okay, so that's a bit of a a little bit more detailed explanation on position vectors. Now, there's a reason we use position vectors, and it's not just to quantify distances, it's actually more to quantify directions. And you may think, well, we already have a distance, right? That should be enough to give us the direction. What's the point? And the point is that the position vector allows us to understand the direction of 2 points if we have a physical location from those 2 points. In other words, if I have my physical location, I'm standing right here, and then what's your name, Christian Campus guy?
Ethan.
Ethan. So if my physical location is here, and Ethan's physical location is there, my position vector essentially gives me the distance between myself and Ethan, right? But I don't need that distance just because I want that distance. Let's say that I want to apply a force. Let's say that I want to throw a marker at Ethan. I need to know in which direction, mathematically, right? Because that's how our brains think. We need to know mathematically in which direction to throw this marker. And that's why we use the position vector. So I can use a position vector to figure out the direction in which I have to throw my marker. And then I just apply that directional vector to the magnitude of a force, and then I throw my marker at you. I need a little bit more force, but essentially the direction was correct, right? Thank you, Ethan. So essentially, that's what the position vector is for, okay? I typically use it not necessarily to quantify length, but to understand directions. And we'll see in a few seconds how we can use the position vector to quantify directions. But before we move into that, I want to I want you to get an idea of vectors as a product of a scalar and something with direction. You may say, wait a minute, what does that mean? Let's look at a force vector F. You know that this arrow represents that it's a vector. Instead of just looking at this and saying, well, yes, it's a magnitude and a direction, you can actually explain that definition or express that definition mathematically. So if my vector is F, and the magnitude of F is simply just F but without the arrow, I can say that my vector F is equal to the magnitude of F times a unit vector in the direction of F. And you might say, wait, what's going on, right? Why are we adding so many variables to what should be a simple vector? So think of it this way. My vector F is a force vector with magnitude and with direction. But now instead of looking at F simply as a number or a number and a direction, I want to look at it as a product of two quantities. This quantity, u hat, is simply a unit vector, right? Remember, the hat represents a unit vector. So u hat is my unit vector in the direction of F. So if I were to draw this u hat, it's simply a small unit vector with a magnitude of 1 that's in the same direction of my force. And then if I multiply this vector by my magnitude F, if I multiply F times the unit vector, I'm essentially scaling the vector, the unit vector. But you guys remember on week 1 when we started, or on week 2 when we started looking at vectors, we said that 2 times vector A is essentially just doubling up the size of the vector, right? If we multiply vector A by 0.5, what are we doing, Madison?
Just scaling it.
Yes, scaling it, right? We scale it down to half its size. If we multiply it by 4, we're scaling it to 4 times its size. So if we multiply a unit vector that has a magnitude of 1 by F, the magnitude, we're simply scaling this unit vector to the size of F. So essentially, I'm looking at this vector as a product of two quantities, my F scalar and my unit vector in the direction of F. And again, this may seem like I'm trying to complicate things, right? Because we already have this. Why do we need this? But if we can see vectors this way, it's going to help us understand these next couple of lessons a little bit better. Because if we were to break down our vector F to our rectangular components, do you remember the rectangular components? What were they? X, Y, and Z, right? So I can break down my F into Fx in the X direction, Fy in the Y direction, and Fz in the z direction. This is what we call the Cartesian vector notation, right? From week 2, I think, or week 3. Essentially, if you look at these terms, these are not that different from this formulation. We have a scalar quantity, that's fx, multiplied by a unit vector. Except that this unit vector, we already know the direction, is just the x direction. We have a scalar quantity, fy, multiplied by a unit vector. We have a scalar quantity, fz, multiplied by a unit vector. So all vectors really can be looked at as simply products of a scalar and a unit vector. This I is simply a unit vector in the x direction, right? This j is a unit vector in the y direction, and so on. So this formulation is essentially our way of quantifying Cartesian coordinates. And it works, because if you look at the individual rectangular coordinates, if you guys remember how to add vectors, when we add vectors, we're essentially drawing a vector. Let's call this fx. And then drawing another vector that starts at the end of the first one, it's fy. And then drawing another vector, right? fz. And my final result, simply f. So we did this, right? We did this on week number 2. But essentially, I want you to look at vectors as combinations or products, of scalar quantities and unit vectors. Now, if a vector is a product of a scalar quantity and a unit vector, then the question is, how can you find your unit vector? You know that the unit vector is supposed to have a magnitude of 1, and it's supposed to have a direction. So in order to explain how we're going to find these unit vector quantities, let's first look at some of the unit vectors that we're already familiar with. Let's start with unit vector I. Thomas, what's the direction of the unit vector I?
Horizontal?
Yeah, along the x-axis, right? Let's try not to use horizontal vertical here. Let's just use x, y, and z, okay? But along the x-axis. So if I were to express my unit vector I in rectangular coordinates, I would have some quantity along the x-axis plus how much does this unit vector move in the y direction?
0.
0. So it's 0 in the y direction plus how much in the z direction?
0.
0 in the k direction. Now what's the magnitude of this unit vector?
1.
So what does this magnitude have to be? 1. So in Cartesian notation, this is my unit vector I. And how can you prove that it's a unit vector? Find the magnitude. The magnitude of I is equal to my x component squared plus my y component squared plus my z component squared, right? Because vectors form triangles, and if they form triangles, we can apply the Pythagorean theorem to them. So let's just solve this quickly. What's the magnitude of the x component? 1. So 1 squared plus 0 squared plus 0 squared. How much is this?
1.
1. So if the magnitude of my vector is 1, then I am dealing with a unit vector. We can do the same thing for j. We can do the same thing for k. But those are easy because those vectors will always be a combination of 1s and 0s, right? I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. It gets a little bit more complicated if I am dealing with vectors that are not necessarily in the x, y, or z direction. So vectors that can be in any arbitrary direction. And that's what we're going to learn, how to find unit vectors in any direction. So let's say that we want a unit vector for any vector. What's your name?
Kyle.
Sorry?
Kyle.
Kyle. Give me the name of a vector. Give me a variable or something. I. No, not that.
Okay.
Not K. Something that we haven't used yet.
V.
V. Okay. So let's say we want to find the unit vector that corresponds to a vector V. So I have my vector V here. I'm going to draw it. Here's my vector V. And just to make things fun, let's call this a velocity vector. Okay, so we have velocity vector V. We want to find the unit vector that corresponds to the velocity vector. Who's sitting next to Kyle? Ryan. Ryan, if I say the unit vector that corresponds to velocity vector, you can tell me if I'm right or wrong. I'm looking for a vector that points in the same direction as my velocity vector. Is that correct? Okay. And I'm looking for a vector that has the same magnitude as that velocity vector. Is that correct? No, right? What's the magnitude of my unit vector? Just 1, right? So I'm looking for a vector that's in the same direction, but has a magnitude of just 1. Okay? You'll see magnitudes expressed as the variable without the arrow or hat, or you can see them expressed as the variable with the arrow or hat in between 2 brackets. So there's different ways of quantifying or showing magnitudes. So I want a vector in this direction, but with a magnitude of 1. And there's an easy way to find the vector. What happens if I divide these 3 terms by the vector's magnitude? I get 1 over 1, and how much is that? Just 1. 0 over 1, 0. 0 over 1, 0. So if I divide the vector by its own magnitude, what I'm doing is essentially I'm canceling out, or I'm eliminating any semblance of scaling in that vector. And what I end up with is just a vector with a magnitude of 1. So let me express this mathematically. Maybe it's a better way to express it mathematically. The unit vector is simply taking your vector and dividing it by its magnitude. If you take any vector and you divide it by its magnitude, you're going to get a unit vector with essentially a magnitude of 1. So let's try it out. Let's put some numbers into this unit vector. What's your name?
Sanders.
Give me a number.
2.
2? All right, so let's say that my vector v is 2 in the x direction. Give me a number.
5.
5 in the y direction. Give me a number.
8.
8 in the z direction. If I want to find the unit vector of this velocity vector 2, 5, 8, I need to divide the vector by its own magnitude. All right? You, sir, all the way in the back. Yeah, you. How do I calculate the magnitude of this velocity vector v?
You square them on, add them up.
Exactly. You square them up. You add them up.
You take the square root.
And then you take the square root. So essentially, I have my vector on top. I have my magnitude on bottom. Is that correct? Okay. So let's go ahead and start solving this. What's the magnitude of this vector? We got 2 squared, that's 4, plus 25, plus 64. How much does that give me? You can use your calculators if you want. You don't have to go all right.
I believe it's 93.
What?
I believe it's 93.
So Raymond says 93. Can somebody with a calculator confirm?
What is my nickname?
It's an old movie. You're probably too young to have seen it.
Okay.
It's 93.
93? Okay. Good job, Dustin Hoffman. 93. Here we go. You take the square root of that to get the magnitude of the vector, right? And then we have our velocity vector on top. Now, if you look at this, you may be confused because we've never done this operation before in class, but it's actually not that different from any algebraic operation that you've done before. When you have 3 terms divided by a term, this, mathematically speaking, is actually the same as me saying 2i over square root of 93 plus 5j over square root of 93 plus ak over square root of 93. Does that make sense? Because we have 3 terms on the numerator, 1 term on the denominator. It's just the same as taking each individual term and dividing it by the denominator and then adding them up. This is math, right? We're not doing anything magical or anything here. So let's start plugging in numbers. If you have your calculator, then what's 2 over square root of 93? And try to give me, I don't know, give me 5 decimal points, just so we can get an answer as precise as possible.
0.20739.
Okay. What's 5 over square root of 93? Somebody else.
Uh, 0.5185. Oh, you said 5 decimal places?
Yeah.
848.
All right, let's do 8 over square root of 93. Somebody else.
0.82956.
Okay. Assuming that I did all my math correctly, sometimes I make mistakes, but assuming that I did my math correctly, the unit vector for my velocity vector v is right here. But how do we prove that that's really a unit vector? What can we do? What properties do we know of this unit vector? We know that it's in the same direction. What else do we know about a unit vector? Any unit vector. Exactly. The magnitude is 1. So in theory, if I take the magnitude of this unit vector, it should give me 1. So let's calculate that. How do I calculate the magnitude of this vector? Just take the terms, square them, add them up, take the square root. So I'm going to do that. I have the square root of 0.20739 squared plus 0.51848 squared plus 0.82956 squared. I wanted a lot of decimal points because there's always going to be some rounding error, so I wanted to get as close as possible to the correct answer. So somebody plug these numbers into the calculator, and let's hope that it gives 1, right? Otherwise, I'm not doing my job right. So what does this give us?
1.00001916.
Safe to say that this 0.0001 is rounding error? I think it is. You see, with any unit vector, if you were to just plug in these numbers, then you would have gotten exactly 1, right? But essentially, that's unit vectors. You get a vector that's moving in the same direction as the velocity. And how do I know it's moving in the same direction as the velocity? Look at this operation. If I look at this operation, essentially what I'm doing is I'm multiplying my velocity by 1 over square root of 93. So all I'm doing is I'm scaling that velocity vector to 1 over square root of 93. So because I'm only scaling the vector, I'm not changing its direction, I know that this unit vector will have the same direction as the velocity, because all I'm doing is scaling it. And because my magnitude adds up to 1, then I know that my vector is a unit vector. So are there any questions about just general unit vectors, or what they're used for, or at least what they mean? No? I think we all seem to be in agreement of what unit vectors are, okay? So we have a unit vector. We know how to calculate unit vectors. You take your vector of choice, you divide it by its magnitude, voila, you have your unit vector. So now I want to ask you, and I'm sorry for you guys, but I'm using this board because that's what the camera is recording. So if you can't understand something, just let me know and I'll try to write it bigger, okay? But now I want to ask you, if I know how to find the unit vector for any vector, then can I find the unit vector for a position vector? Let's make it easy. For a position vector from A to B, what would this equation look like? Don't give me numbers, right? Just give me the general terms in the equation. What are we going to have in the numerator?
What?
It'd be I and IB.
Yeah, just the position vector, right? The vector on the numerator. What do we have in the denominator?
Square root.
The magnitude, right? Which is just the square root of its Cartesian, or sorry, rectangular terms. So this is our way of calculating the unit vector of a position vector. Now, of course, this can really be applied to any vector, right? We just did an example for a velocity vector. It doesn't matter, right? The math is still the same. But for the purposes of this class, we're going to focus on the unit vector of a position vector. Yeah?
Why do you not put absolute value bars around RAB when you're talking about magnitude?
Just as a preference, but we can do it if that's... the question was, why don't I use absolute value bars? And for my online students. It's really just a preference. So
That's just what I'm used to in physics and calc.
if you're used to, we can just use that in class. So another way of expressing magnitudes is by actually using the arrow and then using absolute value terms. So whichever term you prefer, I'm good with it. For statics, and you'll notice in future classes, we look at any value that doesn't have a direction as a scalar. So if we were to do this, we would basically be adding absolute value bars to any value. That's why I tend not to do this. Because after test number 1, we're going to be dealing with a lot of quantities. Not all of them are scalars, right? So we don't want to add bars to everything. But just to avoid any confusion, this is essentially a magnitude. And any variable that I write that does not have an arrow or a hat on top is a magnitude. You need to think of it as a magnitude. Any scalar quantity, just think of it as a magnitude. So why do we need the unit vector or a position vector? At least for statics, we're going to be focusing mostly on force vectors, right? We're going to be focusing on forces because the point of this class is to find balance between forces. So one of the reasons we tend to use the unit vector and the position vector is so that we can express a force in Cartesian notation. So let me explain. Let's say, once again, that I want to throw something at Ethan. Sorry. I want to throw something at Ethan. And let's say that from physics, I know the force that I need to apply to this marker to throw it at him. So let's say I know the force, okay? So I know the magnitude of my force, okay? Just the magnitude. Just knowing the magnitude isn't enough for me to formulate my throw into a mathematical expression. In addition to knowing the magnitude, I need to know the direction. So is there a vector that can give me the direction between myself and Ethan? What is that vector called?
Resultant.
No, we just talked about it. Just the position vector, right? Yeah. So I need to know the magnitude of my force, and I'm not going to use the absolute value bars for this one. Sorry. And I need to know my position vector. If I know these two things, then I can use them to express the force of myself throwing this marker as a vector. And you'll see how. I have my force, this is just a scalar quantity, just a magnitude. I have my position vector. Here's me. Here's Ethan. If I want to throw my marker, I can first draw my position vector. I'm going to call myself A, I'm going to call him B. But that's really not enough. Because when I'm throwing my marker, I'm not telling my marker, here, apply this magnitude of force. I'm actually applying this magnitude. So the question is, how can I express this force as a vector in this direction? And here's where unit vectors come in handy. If I were to ask you all the way in the back, if I were to ask you to draw a unit vector, I'm not going to ask you to come forward for obvious reasons, but if I were to ask you to draw a unit vector here, the unit vector for R, so this, you had R. First of all, would you start at A or would you start at B?
That's A.
Okay. And would you maintain the same direction?
Yeah.
Okay. So you essentially have a vector in the same direction, but with a magnitude of 1. Is that correct?
Yeah.
Okay. Now, if I want to write my force as a vector, you'll notice that all I'm doing is taking this magnitude and scaling this unit vector on that magnitude, right? Because if I multiply my magnitude f by my unit vector u hat r, my result is simply a force vector f in the direction of r. So now we're going to learn how to calculate or how to formulate force vectors if you know the direction and the magnitude. And here's how. I know my position vector. I know my force's magnitude. I want to write this force as a vector. So the first thing I want to do is, if I don't have it yet, find the Cartesian notation of your position vector. So express it as in I, j, and k terms, right? So rxi, ryj, rzk. If I have the position vector, then notice that all I have to do is convert this big position vector into a tiny unit vector. So I have to find my unit vector for r. And how did we find the unit vector for r?
This is the
Okay, yeah, you're right. Take your vector divided by its magnitude. My vector is already rxi plus ryj plus rzk. What about the magnitude? How can I express my magnitude in terms of rx, ry, rz? If I give you a position vector with 3 terms, x, y, and z, and I ask you to give me the magnitude of that position vector.
Just do the square root of.
Yeah, say it louder, I can't hear you.
The square root of each one of them squared.
Okay, the square root of the sum of each one of them squared. Thank you, Ray. Okay, so I found my position vector. I found my unit vector in the direction of the position. And now I can find my force vector. And how do I find my force vector? Remember, I said earlier, always look at your vectors as products. Product of a magnitude times a unit vector in the direction of your vector. So I can express my force as the product of a magnitude, that's my f value that I already know, times a unit vector in the direction of that force. And what is the unit vector in the direction of my force? It's just my UR. So once I get this, multiply the scalar quantity times this vector, and that will be my force in Cartesian coordinates. You're going to get your x term, right? Your y term, and your z term. Does that make sense? I know it's kind of hard looking at it with variables, but I want you to get used to this because your future classes, they're going to be full of derivations where there's no numbers. And then at the very end, you start to use numbers. So I want to at least start to get you used to looking at variables, okay? Essentially, these are my steps. Here's how I formulate my force vector, having known a known direction and a known magnitude. Before I move on, are there any questions? If I were to give you an example right now, would you be able to solve it? Okay. Thank you for volunteering. Let's go ahead and work with an example.
Quick question for Professor.
I said not.
Yeah, go ahead.
Question. You said to look at the vectors as the magnitude times the position vector?
As a magnitude times a unit vector.
Unit vector.
Yeah, not necessarily position vector. So always think of vectors as the magnitude times some unit vector. Because you're essentially scaling. When you multiply scalars times vectors, you're scaling, hence the word scalar. Ah, I just realized that. I did not know this. I did not know this. But that's essentially what we're doing. Let's go with example. And this is actually from the book. And it's not really an example. It's one of the fundamental problems. This is fundamental problem 223. Before I start this problem, I do want to note that some students in the assignment, instead of solving the problems 2.1, 2.4, they were solving the fundamental problem 2.1, 2.4. So it's not necessarily the right problem. So make sure that you're solving the actual homework problems. Now these fundamental problems with F are actually really good because they cover the very basics of what you need to actually solve the homework. I've had students ask me, like, how can they succeed in this course? And I would say, obviously watch my lectures, read the notes, read your book, the usual. But before you start your homework, try to complete a couple of these fundamental problems because it's easier to figure out where you're lacking if you do the fundamental problems because they're simpler. They're simpler and they don't have 5 topics in one problem. They're like each of them covers a different topic. So if you struggle with one of them, then you know, okay, I need to review my dot product. Okay, I need to review my scaling, right? So do the fundamental problems so you have an idea of where you need to improve before trying the homework problems. Second thing, again, homework problems, you can do them in groups. And I'm perfectly fine with you submitting just one per group. What I'm not fine with is 10 students working on the problem, or one student doing the homework and then sharing it with 10 others. Because I've seen that, right? I've seen students that essentially just send me somebody else's submission with the name changed to theirs. And it's exactly the same submission. Just write both names and do one submission, because otherwise it's too much to look for me. You've noticed that I give you 10 if you submit it. I take 2 points off if you don't submit it correctly. I take 5 points off if you submit it late. And I'm going to keep doing that for now, but that doesn't mean that I'm not looking at them, right? I'm still trying to look at them because I want to have an idea of which problems you're struggling with. And it seems that for the most part, a lot of you, most students struggle with the same problems. And that's good, because that means that I can focus on those problems. But this can only happen if you're honest with yourselves and with me. If you can't solve a problem, just say, I couldn't solve it, right? Just let me know. Don't just find the solution, write it down, and then make me think that you know the problem. Because when it comes to the test, you know, I'm just going to give you everything, right? And it's better for me to know where you're struggling so we can look at that before the test. Which, by the way, the test is when? Tuesday. Yeah, it's going to be interesting. I'm not too happy that I skipped 2 weeks of class, but I think you'll be fine without me. So problem F223. I'm going to be careful when drawing it because I'm not very good at drawing these things. So I'm going to try my best. But if you have your book, just look at your book for now, and that will help you understand the image. So we have our x-axis, our y-axis, and our z-axis. And essentially, I have a point C, which is located at 2, 3, 0. So x equals 2. And the units are meters. Bless you. Y equals 3. And z equals 0. So here's my point C. My point C is located at 2, 3, 0. And then I have a point A. Point A is located on the z-axis at an elevation of 6 meters. So my point A is located on the z-axis at an elevation of 6 meters. Can somebody give me the coordinates for point A? It's on the z-axis at an elevation of 6 meters.
0, 0, 6.
Yep. 0, 0, 6. So those are my 2 points. I'm not going to draw the whole thing. There's like a complex thing with strings and whatever drawn. I'm not going to draw the whole thing because I don't want to embarrass myself. But essentially 2 points, C and A. And we have a force of 420 newtons acting along the line AC. So along this line, we have a cable or something. Along this cable, we have a force with a magnitude of 420 newtons. Now the problem is, I don't want the magnitude of this force, right? I want this force in Cartesian notation. I want the x component of the force, the y component of the force, and the z component of the force. How do we start? Who was a volunteer? I think you volunteered, right? No?
I didn't say anything.
I think you did. Well, how do we start this problem?
So I would consider each of the points individually.
Okay.
And let's see. So the vector is A to C, right?
Mm-hmm.
So
Okay,
we
so
do C minus A.
all right, let's go step by step. So
Each
you're
component,
looking
so
at
f
the
of
points.
f of x C minus f of x A.
We're getting there. I think you're skipping a couple of steps. So you have the right steps. You're just trying to do them all at once. Let's break it down into simpler steps. You said you want to consider both points individually. That's good. And then you said that there's a vector between these 2 points. Good. When you have 2 points, when you have a physical location, a physical distance, what vector can we use to represent this physical length?
AC.
The position vector, right? So we're going to draw our position vector from A to C, like where I said. And now we can go back. We said if the position vector starts at A and ends at C, then what are we subtracting?
C minus A.
C minus A. So we're going to have our position vector, which goes from A to Z, and that's equal to C, the C coordinate minus the A coordinate. I'm going to write the whole thing, not because you have to write it, but because I want you to know where all my numbers are coming from. Okay, so we have my position vector, and let's start punching some numbers in here. What's the x coordinate of point C?
2.
What's the x coordinate of point A?
Okay.
We can do the same thing for y, 3 minus 0. What's the z coordinate of point C? Okay. Good. So what is my position vector? We got 2. We got 3 minus 0, 3. And then we got 6. Is this right?
Negative 6.
What's wrong?
Negative 6.
Exactly. 0 minus 6 is negative 6. So I have my position vector from A to C, which is 2i, 3j, 6k. Is it enough if I just take this vector and multiply it by the force? Is that my answer? What do I have to do in between? Yeah, find the unit vector, right? So I want my unit vector along RAC. Now we've already done an example of this before, so I don't think I should ask, but I will anyway. How do I calculate this unit vector? Speak louder, Ray, I can't hear you.
The 2i plus 3j minus 6k in the numerator.
Okay, so in the numerator we have our position vector, right, which is 2i plus 3j minus 6k. What about the denominator, Ray?
And it would be the square root of the sum of those coordinate vectors.
Exactly, so the magnitude, right?
Yeah.
Magnitude of the position vector, which, like you said, is the square root of the sum of these coordinates. Now, be careful. We have negative 6 here. That doesn't mean that you're going to write a negative sign here, right? Your negative 6 has to be squared. So keep that in mind, right? These terms are always going to be positive because even if they're negative numbers, you're going to square them. I've seen some mistakes where you have 3 squared minus 6 squared, and then they forget that the minus actually turns positive. So I like to write it this way. I like to write plus, 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 and just whatever negative sign, just put it inside a parenthesis just to avoid confusion. All right, I see some people plugging in numbers into their calculators. Can anybody just give me the final answer?
2 7 pi plus 3 7 j plus 6 7 k.
Like this? Is that correct? Can somebody help me with this? What's wrong here? Yes, the magnitude is 7. What's wrong? Yes?
He lost the sign off into 6.
Exactly. Remember, you have 2 plus 3 minus 6. So don't forget that. Where the sign always turns to positive is on the square root because you're squaring your terms. But up here, you're not squaring any terms. So there's no need to get rid of your negative sign. So you have your unit vector, 2 sevenths, 3 sevenths, 6 sevenths, minus 6 sevenths. Before we move on to the final step in this problem, are there any questions? American mask, are you good?
Yep.
Any questions?
So what was that like question initially asking?
What is f in Cartesian coordinates? So f of x I, f of y j, f of z k. So I want to express f in Cartesian coordinates. So American flag, what's the next step?
Next step is going to be multiplying that unit vector by the magnitude of f.
Okay.
Or if you want, you could double check to make sure that unit vector is correct.
Okay. I like that. I like that you're always thinking ahead, right? So you know that we can first double check. So let's do that first. Let's double check to make sure that this actually has a magnitude of 1. How do we check if this has a magnitude of 1? We just take the magnitude of the vector, all the terms squared, add them up, take the square root, and it should give us 1. And because we're using fractions and not decimals, there shouldn't be any rounding error, right? As long as you punch everything correctly into your calculator. So let's go ahead and check that. Can somebody punch those numbers into your calculator and tell me if it's indeed 1? Remember to do the fraction before you square the term, right? Or square 2 and then square 7, but don't square 1 and leave the other one.
And it is 1.
Okay. And it is 1. Okay. So that means that this is a unit vector. Good. So let me put this on the side. I guess I should have included it as part of the steps, but really it's more of a check. Okay. But you always want to do that. I think that's a very good practice, right? Make sure your answer is correct before moving on to the final answer. So finally, you find the Cartesian notation of the force by multiplying your magnitude, your desired magnitude, times your unit vector. What's my desired magnitude? 420 newtons. And I want to multiply this by my unit vector, 2/7 I plus 3/7 J minus 6/7 K. Now this problem is actually a little bit easy because 420 can be divided by 7, right? Yeah, it's 60, right? Over 760. So this will actually be pretty easy. I think you don't even need a calculator to calculate. So what's our x term? What's 420 times 2 over 7?
120.
Sorry?
120.
Exactly, 120. 3/7.
180.
Negative 6/7.
360.
Is that it?
Negative 360.
There we go. Good. Now obviously not all problems are created equal, but I think this one was a little bit easier on purpose so that you don't even need a calculator to actually get this done. In fact, if you notice, the only hard algebra here, the only hard arithmetic here is just this, which ends up being 7 anyway. So this is I love this problem, right? Because this is an example, a fundamental problem where you can't really make a calculator error because you don't need a calculator to solve it. And that's why I like these fundamental problems, because they're not testing you on your knowledge of how to use a calculator. They're testing you on your knowledge of how to actually apply the material. So my Cartesian notation for this vector is 120i plus 180j minus 360k. Are there any questions with this topic before we move on to the next one? Yeah, go ahead.
Does a unit vector have a unit itself, like meters or newtons?
So the question is, does a unit vector have a unit itself? And let's look at that mathematically. We defined my unit vector as simply a vector divided by its magnitude, right? Let's say this vector is velocity. What are the units of the velocity vector?
Meters per second.
What are the units of the magnitude of velocity?
Also meters per second.
What are the units of the unit vector?
Okay, so 1.
Dimensionless, right? So my unit vector is a dimensionless quantity. That's a great question, okay? Unit vector is dimensionless because you take a vector, you divide it by its magnitude, you're essentially canceling out the units of the vector. If you're not sure if that the magnitude has the same units as the vector, just calculate your magnitude and plug in your units here. You'll notice that you'll still get the same units. It's not going to change, okay? Good question. What's your name?
Will.
Will. Good question, Will. Any other questions before we move on? No? So are we ready for the test then? Are we?
No.
I mean, if the test were just on position and unit vectors, are we ready for the test?
Yes.
Are you sure?
Yes.
Okay. I'll keep that in mind when I complete the test. We have 15 minutes, and I mentioned the first day that I'm going to make use of all 75 minutes of this class because there's a lot of material, right? So there is no leaving early. So what I'm going to do now is I'm going to start the last topic of this test, which is section 2.9, also known as the dot product. I don't think we'll have time to get into the deep mathematics of the dot product here. I don't think we'll have time to do an example today, but at the very least, I would like to at least define it. Because when I learned the dot product, I think I learned it in high school math or something. I don't know. Probably high school. But when I learned about the dot product, I was never really told what it was used for or what it meant. I was just told, here's how you calculate it. Go figure. So dot product has many applications in many different fields, but we're mostly engineering majors. And because we're engineering majors, we care about the engineering or physics application, physical applications of our mathematical quantities. In this case, when we're talking about dot product, we're essentially talking about a multiplication of two vectors. Now, when we're looking at adding vectors, we said that if we add two vectors that are in the same direction, A and B, I say A plus B, essentially we get a new vector, C. That's how we add vectors in the same direction. But if the vectors are in different directions, so let's say we have A and B, then my C is actually just this vector, right? And we still get A plus B equals C. So that's adding. Things become a little bit more complicated when we're multiplying. In fact, they become so complicated that we need two types of multiplication for vectors, right? Dot product and cross product. So today we're going to talk about dot product. And I'm going to try my best to explain what it means physically. I'm going to say my best because I've never done this explanation before, and you may not understand it even after I explain it, but I'll try. Essentially, there are two ways of multiplying vectors. You can multiply two vectors that are in the same direction, just like you multiply two magnitudes, right? So you can multiply A times V and get a vector C. If A is 4 and B is 5, right? The magnitude of C should be 20. 4 times 5 equals 20. It's not going to be 9, right? It's going to be a little bit more, 20. So I can say A times B equals C. But the problem is, what happens when my vectors are in different directions? Here is where multiplication for vectors gets a little bit complicated, because there's no easy way of saying, well, we're going to multiply these two values and then get a vector in another direction, because physically it's kind of hard to come up with a standard. So what the dot product represents, and try to draw it a little bit bigger, what the dot product represents is for two vector quantities that are in different directions, my dot product tries to first express those quantities in the same direction. That's the first step. And how do we do that? What we're going to do is we're going to find the component of B along A, the component. Do you guys remember components, right? So the component of B along A will be this one. I'm going to call it B sub A. And now I have two vectors in the same direction, and then I can multiply them. And that's the dot product. Let's say that the angle between A and B, you can see the A direction here. Let's say that the angle between A and B is theta. What is the component of B along A? Like, how can I calculate this component if I know that this is theta and I know this B vector?
Sine times theta?
Cosine theta, right? Not like cosine theta, right? Because you have a vector, you have the angle along which you want to project it, and then you use trigonometry, right? This is the right triangle. This should be equal to the hypotenuse times the cosine of the angle. Does that make sense so far? Do you know why it's cosine and not sine? Okay. So this component BA is just B times cosine of theta. And it's a vector in the same direction as A. Now, if the vector is in the same direction as A, and I want to multiply them, all I do is multiply these two vectors. In other words, all I do is multiply vector A, or the magnitude of vector A, times the magnitude of my B sub A, which is just B times cosine of theta. And that's the general definition of the dot product. Now you're going to say, why that? Why are we looking at components of B over A? Why can't we say B times A is equal to the component of A over B? So let's look at that. Let's say that instead of looking at the component of B over A, let's say that I want to find the component of A in the direction of B. So I have my little vector here. I'm going to call this A sub B. And again, I know that my angle between them is theta. So vertical angles, this is theta as well. How do I calculate this a sub b? Let's see, I have a hypotenuse. I have a right triangle. Okay, say it louder.
A cosine.
A
Base.
cosine theta. So I have two vectors in the same direction. A cosine theta, b. And now I can multiply them in the same way. I have my vector b. I multiply it times my projected vector a. And my projected vector a is simply a cosine theta. What's the difference between these two? There is no difference, which means that the dot product is commutative, right? A dot b equals b dot a, because this product will be the same. Now we want to say, why? Why do we want to do that? What's the use of multiplying over components? And here's the thing. When you have two physical quantities that you want to measure, or you want to measure the effect of one on the other, and those physical quantities are not acting in the same direction, then you cannot, right? You cannot apply a full physical quantity into a second one. You need to always express it in terms of the same direction. For example, what is work? You guys remember work from physics? What is work? What is work?
A force that results in motion.
All right. And how do I quantify that work using that force?
FD.
FD, right? So from physics, we know that F times D equals work. But, there is a but, right? This equation is only valid if my force and my direction are in the same line. How can I quantify work if I'm applying a force in one direction, but my actual direction of application of the work is in a different direction? How can I do that? Can I use this equation? Not quite. But then there is a way to multiply values if they're in different directions, right? And that's the dot product. So if my force and my direction are in the same direction, valga la redundancia, if my force and directions are in the same direction, then I can use this equation. But if they're not, then I have no choice but to treat them as vectors. And then my work is actually force dot distance. And that's how I calculate work physically for two vectors that are not in the same direction. And you may say, how do we go from here to here? It's actually pretty easy. F dot D is the magnitude of F times the magnitude of D times cosine of theta. If the force and the direction are in the same line, what's the angle between them?
0.
And what's the cosine of 0?
1.
So F dot D is equal to F D cosine of 0, which is just 1, which is just FD. And this is where this equation comes from. So the equation that you learned in physics comes from the dot product. Doesn't matter whether you've used the dot product or not, you have, right? Even if you haven't literally written a dot, you've used this. You've just used it for vectors along the same directional line. What else? Power, right? Power. What is power? Let's go back to physics.
Work over time.
Work over time, right? Work over time, or just force times velocity. Same dimensions, right? So power is force times velocity. Again, if my force and the velocity are in the same line, this equation is correct. But if they are not along the same directional line, then I have no choice but to treat my power as a dot product of two vectors, a force vector and a velocity vector. So what the dot product does is it essentially helps us quantify the effects of one physical quantity upon another if their directions are not the same. It's going to be very important when we go up to fluid mechanics, when you go up to solid strength of materials, when you start to deal with classes where quantities are very important and directions are very important, you'll notice that you'll find yourself doing more dot products and less scalar multiplications. So that is essentially the physical meaning of a dot product. The effect of one physical quantity upon another when they act along different directions. Any questions with the dot product? I know it's I get excited, right, when I teach about these things. So I'm almost out of air. Yeah.
Can you say that definition again? About here's that little
Let me
thing.
read it. A dot product is the effect of one physical quantity upon another when they don't act along the same direction. Now, obviously, if they act along the same direction, you can still use the dot product. But at that point, it's maybe just easier to just write the scalar equation, right? But that's how I would define dot product. It's not the best definition because there's other ways to define dot product from a mathematical term, from a other fields term, right? But I care more about the physical definition because that's essentially what you're going to look at when you graduate, right? You're going to look at physical definitions, okay? So we define our dot product as the product of the two magnitudes times the cosine of the angle between them. Now, from a statics point of view, I already explained the physical point of view, right? And you can use power and you can use work in your engineering, but specifically from a statics point of view, why do we care about the dot product? Because in statics, we're not really looking at power, right? Because we don't have moving things, right? From statics, we can see a couple of things. If we have two vectors defined, that means that we know their Cartesian coordinates, or their Cartesian coordinates. Could we find their magnitudes? If we have two vectors and we know their coordinates, okay. So now, if I have two vectors, and I know their Cartesian coordinates, you're all saying that we can find their magnitudes, right? So now, if I know the vectors, and I know their magnitudes, can I use this expression to find the angle between them?
Yes.
Yeah. And that's what we're going to use the dot product for in this class. We're going to use it specifically to find the angle between two vectors, right? Where my angle is simply the inverse cosine of the dot product of these two vectors over the product of the magnitude of the two vectors. And you'll say, wait a minute, this is kind of repetitive because we're using the dot product, right? So we need to apply the definition again and again and again. But we'll see that there's an easy way to calculate the dot product with Cartesian coordinates without needing to resort to this equation. And once we learn that way, we will be able to calculate any angle between any two vectors without having to worry about using calculus or all that stuff. Any questions related to the dot product? It is 6:12. We have 3 minutes left. Should I let you go? Of course not, because again, we have a lot to cover in this class. I'm trying to figure out something that I can do in 3 minutes, because I really don't want to let you go. 2 minutes. I can't find anything. Just go. The lecture videos are late. This will be the first lecture video. I'm going to upload Thursday's lecture video as well, so you may have to wait until Thursday night or Friday morning to see Thursday's lecture video.